All right, next thing we've got up is the charging of a capacitor. So here I have a really simple circuit. I've just got a battery hooked up to a capacitor. What's going to happen is as charges begin to flow, negatives will flow off of here because we know negatives are what are actually flowing. Looks the same as if positives were flowing, but we know electrons are the only part of an atom that can move, or at least can jump off of atoms and move around. So negatives come over here and build up. When they build up, what's going to happen is they're going to push away on the electrons on that side, moving them over to the positive. Same idea, the positive here is going to pull the electrons towards it. So you'll end up with the same charge on both sides, just the opposite sign. So if you leave it for long enough, eventually the voltage across your battery is going to equal the voltage across your capacitor. Cool beans? Simple enough. But capacitance is going to be how well it stores charge. So capacitance, for different amounts of for a different voltage that's going to push the charges away, different materials are going to have a different amount of capacitance. It's also going to be affected by the size and area, but we'll get into that for us in a second. Right now, let's just look at what capacitance is. So capacitance, C, is equal to the amount of charge you can store per amount of voltage that's pushing the charges around. Capacitance is measured in farads, which a farad is just coulombs per volt. So F farad, that's basically what it is, coulombs per volt. And hey, check it out, F equals Q over V, C over V. Cool beans. And usually we measure this oftentimes in picofarads or nanofarads. Remember, pico is just minus 10 to the 12. Nano is minus 10 to the minus 9. The reason for that is most of the time we end up with really, really small capacitances. If you end up with higher ones, like you have to make your surface area ginormous, but we'll get into that in just a second. So when we look at here, what is capacitance determined by? It's going to be determined by the geometry. Almost forgot to spell it. The geometry of the capacitor. I did not give myself a lot of space here, but the geometry of the capacitor. So what things are included in the geometry? Let's take a look. First one is going to be the size of the plates. I guess size is fine. The size of the plates. The next thing, the shape of the plates. Again, that's just going to affect how much surface area. So both of these, you could say the surface area of the plates. And then the last thing is going to be the distance between the plates. We'll get into in a little bit. There's one other thing that can affect it, but we'll get into that in the next section. So let's come over here and, well, we might as well throw it up here. What does the formula for it look like? C equals epsilon naught. Oh, no, Mr. Dillon, I don't know what epsilon naught is. It's just a constant. It's the vacuum, and I got to read this because I'll always say it long. The vacuum permittivity, not permissivity. But the vacuum permittivity, it's just something to do with like how charge spreads itself and how charges can move across space. So this one right here is just going to be, and this is on your formula sheet, 8.85 times 10 to the negative 12 coulombs squared per Newton meters squared. Neat. It's just a constant. We're just going to put it in on stuff. It makes the numbers work. It's because our numbers aren't natural. They aren't related to constants in any way, so we have to do that to cancel it out with our units. Then we just have area, meters squared, over distance between them, the separation. So let's try this out in a problem. Up here, I'm going to kind of draw a line so you can see what's what. Over here, we've got 2 plates that are separated by 1 millimeter. The plate is 20 centimeters on one side, 30 centimeters on the other side. So if you guys think you can solve any of these right now, go ahead and pause the video and do it. But if you want to see me go through them, just let it keep playing. If there's any point you want to try it out, just pause the video and then we'll go through it. So on this first one, we want to find what is the capacitance of our capacitor. Simple enough. Let's just plug it into the equation. C equals epsilon naught A over D. Epsilon naught is 8.85 times 10 to the minus 12. I won't worry about that disgusting unit. Area is just going to be this times this, but remember, we need to be in units of meters, so we'll have to do some conversions. This will be 0.2 meters times 0.03 meters. That's our area. Now we need to take it over the separation between them. Millimeters is thousandths of meters, so I need to move the decimal point 3 times. There we go. And when we plug that in, I get a capacitance of 5.3 times 10 to the minus 11 farads. Now, like I said, these are often really small numbers, so go ahead and try to write this out in terms of picofarads. Take a second, pause the video, write it down. Did you do it? Nice job. Well, since minus 12 is pico, that means this is 1 decimal bigger than it, so this will just be 53 picofarads. Hey, that's pretty neat. All right, next up, we want to find what is Q if our voltage across it is 12. Simple enough, we use our capacitance formula right here. C equals Q over V. We'll rearrange it. Q equals C over V. When I do that, I get my capacitance is 5.3 times 10 to the minus 12 over 12 volts. And when I plug that in, let me check my numbers over here. I get 6.37 times 10 to the minus 10 coulombs. That's a very tiny amount, not a lot of charge on there. For this next part now, we want to find what is the electric field between them. So remember, electric field is just delta V over delta R. We know the separation between them is a millimeter. We know the voltage is 12, so we just put 12. This is a little throwback to the last unit here. 0.001 meters. When I plug that in, I get 12,000 volts per meter. And then finally on this last part, we want to find what area we would need if now the plates were only 10 micrometers. So that's a lot smaller, 10 micrometers apart, and we wanted a capacitance of 10. So now we're solving for area. Capacitance equals epsilon naught A over D. Rearrange this to solve for A. We get capacitance times the separation over epsilon naught is equal to our area. Capacitance is 10 farads. That's a big amount of capacitance. Our separation is 10. Well, let's just write it out and make it easy. 10 times 10 to the minus 6th because it's micro. And then we're dividing by 8.85 times 10 to the negative, 12? Yes, it is. When we plug that in, what we're going to get is let me check my numbers here, 1.13 times 10, wonderful, to the 7th square meters. Now you're like, Mr. Gillum, that seems relatively large because that's like a plate that has about a 3.5 kilometer side. So if we made a square out of it, it would be 3.5 kilometers on each of its side lengths. So you're like, well, how do we get actually large capacitances for real things? Well, 2 things. One, they're actually going to wrap capacitors up, and I'll show you guys later on that capacitors kind of get tucked together and made into almost like a burrito, so that way you can store a lot of surface area in a small amount of space. And the thing we're going to see in our next unit is a dielectric. So if you increase the value of the resistance, or if you increase the strength of your resistor in between the plates, then what you find is you can get a lot higher values for capacitance. But that's all we've got on this section for charging a capacitor.